We'll start with the simplest example, the electric field produced by a single point charge Q. The definition of the electric field suggests we can calculate the electric field produced by this charge at some point P by determining the force it would exert on a unit positive charge located at point P. The first thing to notice is that the direction of this force will always be radial, pointing outward since like charges repel. Consequently, the electric field at any point will also always point radially outward from Q. As we now move further away from Q, the magnitude of the electric field will decrease, since the Coulomb force is inversely proportional to the square of the distance from Q. We now plot E, the magnitude of the electric field produced by Q, as a function of r, the distance from Q, i.e., for every value of r on the horizontal axis, the corresponding value of E is plotted vertically above it. We see that as we move away from the point charge, i.e. increasing r, E decreases, and as we move toward the charge, i.e. decreasing r, E increases. For example, if we increase r by a factor of 2, E decreases by a factor of 4, since the electric field of a point charge is inversely proportional to the square of the distance from the charge. It is interesting to note that this solution is consistent with the spherical symmetry of the problem. In particular, a single point charge must produce a spherically symmetric field. That is, the spherical charge looks identical from all points that are the same distance from the charge. The magnitude of the field can only depend on r, the distance to the charge. We'll now take a brief look at another example that does not display this symmetry.